Hi, and welcome to the fourth lecture of the control course. This one is about PID controller. So PID controller is one special kind of control system, the control system that we've seen in the second lecture, and now we're going to give this details about one very specific kind of controller. And the thing is, why are we talking about this? Why are we talking about PID controller? Well, PID controller is actually widely used in industry for really anything. Like it's used in the car industry, it's used for robotics, chemistry, everything is like that's food related. So it's really like a kind of controller that is extremely used in the industrial setting. So now we want to get into deep with the PID controller, understand what it does, what are its components and its advantages and also its disadvantages, because of course it's not perfect, otherwise there would be absolutely no reason to study control theory, and try to understand when to use the various types of PID controller that we will present in this lecture. So first we start with PID. What does it mean? Well, PID stands for proportional, integral, and derivative. So it's three components of the PID controller, which we'll try to explain in details in the next slides. So just to give the gut feeling of what we're talking about, we have the proportional controller that acts on the present error. So it's something that is proportional to the error. And this is something quite similar to what we've seen in the first lecture about control and also with the bicycle, where we have an error and we have a constant that multiplies that error, and that's our controller. So this is an idea which is actually quite similar to that. Then we have an integral part. The integral is something that considers the average of past errors. So it takes into account the past. So it's something that you can imagine as you see that the error is decreasing over time, and so you take that into account for your control action. You don't just depend on what is the error now, but you depend also, like the control action depends also a bit on the evolution of the error, which sounds like something smart to do. And then we have the derivative term. The derivative term can be interpreted as a prediction of a future error. So derivative term is something that looks forward and tries to predict the evolution of the system, and so it also steers the control action towards certain direction. Now, what is the shape? What is this actual PID controller? What's its formula? Where this is the formula. So we have the input, and the input has a proportional term, which has a proportional gain, which is k, multiplies the error. So actually now if we forget about everything else, this is exactly what we've seen in past lectures. Then there is this integral term, which depends on the proportional gain, but also an integral time constant. And this is the integration from 0 to t, so basically takes into account all the past errors. And then we have this derivative term, which has the derivative of the error. And so it's like a sort of error velocity, how the error is evolving. And it also has a derivative time constant. Of course, this we can rewrite if we don't want to make everything depend on Kp and just say there are three gains. There's the proportional gain, integral gain, and derivative gain. So this is the generic shape of a PID controller. And when we insert it in our block scheme, this is how it feels like, this is how it looks like. And you can see it, it's basically everything that we've seen so far. In here now, since we are now on the fourth lecture, I added some more things. So let's go step by step. We have a reference signal that is something you want to either track, or is it a desired state for the system, whatever it is, but this is a reference. And there is an error. It depends on the reference and something else. We're gonna get back on this one. And then the error feeds the PID controller. As we've seen, the PID controller is something that needs present error, past errors, and time derivative of the errors. So we have the PID controller. PID controller then gives an input. And this input is something that technically you should apply to the process, right? But here it's not happening. Why? Well, it's not happening because the world we live in is not perfect. And so if you have a system, which is the PID controller, we said in one of the first lectures that the controller is also a system. So if we have a system that gives you a signal, like you are usually not really able to take that signal and feed it to another system as is. Usually there's always some problem, there's some disturbance that alters the signal a bit. And so in here I called it DA, which is a disturbance on the actuators, because it's very likely that our controller is something that acts on the actuators, for example, and then we have a disturbance on the actuators that changes the input a tiny bit. So the actual input that is fed to the system we want to control, our PS, is a UA, which is slightly different from U. It's a disturbance, it's there, just have to live with it, and it's something like usually it's a disturbance that one cannot really model, but we will see something about this later in the lecture. Then we have the process. This process has a certain evolution, and it gives a certain output, and this output can also be disturbed by something to get the actual output of the system. So it doesn't necessarily mean that what you have here as output is exactly the output that the system will give, because there might be some disturbance that acts on the system. And then I added something else here, because we always said there isn't the output. The output is something that we want to have as close as possible to the reference, and so we need to measure it. Well, this action of measuring the output means that there has to be a sensor in here which is able to measure this output. And the sensor also, exactly as the actuator, is not perfect. The sensor could have technically some inaccuracies, can be not the best sensor out there, and so there's some sensor noise here that acts on the real output of the system to modify it a bit. This is YM now. It's not just Y, the output of the system, but it's a Y measured. So it's the measured output, which might be slightly different from the actual output of the system. So now this is the most generic block scheme you can have, and like for the first time in the course we now have included everything, or at least most of the things that are actually very relevant when you have a control scheme in terms of disturbances, noise, and everything that you should technically take into account, because the system is not like the word is not as simple as we get a perfect signal that we feed to the system and we get the perfect measurement out of it to feed the controller. So there are always some small things to take into account, because in math you would get that something maybe is stable when then actually something might be not with the control action you compute. Anyways, with this we have how the PID controller stays in the block scheme. So now we're going to have a look at how to use the PID controller and when to use each one of them. What do I mean? Well, we seen that the equation was the input is equal to a proportional term, an integral term, and a derivative term. Then it means that we can just switch off some of the terms. And we can start with the simplest controller, which is the proportional action, the P controller. Where a P controller is just U equal to K error. This is something we've already seen, something we've used also for the neutral model of the bicycle. And it's something that it's just as simple as just we look at the error and we want the control action to depend on the error. That's it. Now, if you take the block scheme from the previous page, from the previous slide, and you try to do the transformation in Laplace domain, you will get that the error can actually be expressed by this equation. So in this case, we did not consider the measurement noise. So the n that was coming from below, you can remove it. You can just see each signal, where does it come from, and you will get that it's basically something like this. So we have that the error depends on the reference, so the Laplace transform of the reference, Laplace transform of the disturbance that acts on the output, and Laplace transform on the disturbance that acts on the actuators. And there's nothing else. So these three are signals that come from the outside of the block scheme. So this is our Laplace transform. And you can see here that if you want the error to go to zero, then these two terms should technically go to zero. Well, when does it happen? We have g. G is a transfer function. So g has its zeros, its poles, but then like it's something that has its own shape. But there's kp here and here. So we can intuitively see from math, from calculus, that if k goes to infinity, then this goes to infinity, and therefore the fraction here goes to zero. Both fractions go to zero. And so basically that's what we want, right? So the error is zero if k tends to infinity. Of course, we cannot have a controller that has an infinite gain. This is not something we can realize, but intuitively that's what happens. What are the pros and cons of such an approach? Well, the proportional controller, when you raise k, so you put k up and up, it has a faster response. So it makes the system faster. So the evolution that you trigger, whatever it is, that evolution doesn't mean that it's the perfect evolution, but it gets super fast. And this, like, intuitively is also, it makes also sense, right? Imagine in the case of the bicycle, when at some point we said that the tilting angle was controlled with the steering, and basically the steering that we applied was k phi. So k was a gain and phi was again the tilting angle. So you can imagine that if you're tilting on one direction and then you apply a very big k, it means that you're steering immediately super strongly, and then the bike evolves. And it doesn't mean that it's good, because actually such behavior might cause you to fall down on the other side, but you can intuitively see how this action leads to faster response. Also, the steady state reduces. So if we raise k, technically the steady state error reduces. It doesn't go to zero, because to go into zero, it would need to be infinity, as we've just seen, but it reduces. The cons are instability, and this I think I explained quite well with the bicycle now. I gave you the idea of it, like you have a big K, so you might fall down on the other side. And measurement noise affects the closed loop system, so actually this does not take into account. Okay, so this is the P controller. It's just a proportional, it's the simplest one. So let's have a look at something more complicated. We have the P action, the proportional action, but we also now take the integral action. The integral action is, again, the integral here, and the integral is basically summing the area of the error between the reference and the signal. So it's summing up those that area, and it takes into account for controlling the system. So this means that this is a good thing, because like it looks at all past errors, it sees maybe that the error is reducing, and therefore it's something that triggers the controller maybe to give a smaller input, for example, or like a softer input, because it sees that the system is actually converging where we want. So what are the pros and cons? The first is that this basically counts as an integral gain, as an infinite gain, because it's something that integrates over time with a certain time constant, which is like integration time constant is usually quite small. So this is also a very big gain. So basically this is an action that brings your steady state error to zero. So if you want perfect tracking, asymptotic perfect tracking, you need an integral gain. The other thing is that when Ti is small, so you have an integral constant which is quite small, then the closed loop system stability is harmed. Well, now this already gives quite a good controller. It gives something that reduces that annihilates the steady state error. It also something that gives fast response and everything. So we might be happy with that. So what about the derivative term? What does it do? So the good thing about the derivative term is that it works as a brake for the system, because basically what happens is that it's an anticipation term, because the derivative is something that tells you how the error is going, like what is the behavior, the evolution of the error. It looks like the gradient of it. And looking at the gradient, you know in which direction it's evolving. And so it's something that if it sees, okay, now the evolution is going to be quite steep, it might break down the system in order to not have issues, for example, with overusing the actuators and stuff like that. Of course, it's also not perfect, because derivative term, like a prediction in the future, is something that usually is not realizable. And what it introduces in practice, it's that it amplifies high frequency signals. So if there's some noise, if there's something that like is in the system that is very high frequency, something that gets amplified and can actually harm the actuators. The derivative term has also another problem, that if we look at it, it has a derivative. Therefore, when we put it in Laplace domain, looks like this. And this is not a valid transfer function. As I said, this is a prediction, it's an anticipation in the future, but with something we cannot really realize, we cannot make. So this is something that needs a pole, because the transfer function that we use, as we have mentioned in the first lecture, have zero and poles. The poles are the eigenvalues of the system, and so we need poles in order to realize the transfer function, because something like this would diverge, would be completely unstable. So the thing is that this is basically just a future prediction. It's impossible to know what happens in the future. So we need to realize it. How do we do it? Usually it's done by something like this. This looks ugly, but basically, if you look closely, this is exactly what you've seen here, but there's one fraction more. And this one fraction more has just one pole, which is basically all we need in order to make this possible, in order to make this realizable. And this pole has the exact time constant that we've seen so far, and a certain n, which is big enough. Why? Because if n is big enough, this fraction goes to 0. And if this goes to 0, this is basically 1 over 1. So this kind of cancels off. And so the bigger is n, the closer we are to this shape here that we ideally want, but we cannot really realize in practice. So we are just trying to put, to create a pole that makes this realizable and makes something that is as similar as possible to this. Okay, so we have now got a basic idea of PID. Let's sum it up to the main facts that we said about this. So first, stability. Well, stability is harmed if the proportional controller goes up and up. So we make the proportional gain higher and higher and higher, the stability might be harmed. So remember the example of the bicycle, you are leaning in one direction, you make a super big steer in the opposite direction. This is actually something that makes you fall down in the opposite direction, while if you steer gently, is something that doesn't happen. Integral also, this is something that harms the stability when the integral constant goes down. So when we integrate more, the stability can be harmed. On the other side, we have a brake, and the derivative term acts as a brake to the system, so it's something that help us preserving stability. Then we have steady state error. Steady state error is reduced by high gains in the proportional term. So the higher we go, the lower is the steady state error, but it doesn't go to zero. With the integral gain, however, that actually goes to zero. It's asymptotically zero. There's no steady state error. The derivative term, I didn't say anything about steady state error. It's basically unrelated. There's nothing happening here. Then in the second lecture, we introduced some nomenclature when it comes to the evolution of the system. So we looked at the overshoot, transient, steady state, all those properties that are nice to take into account when controlling a system. What happens to them when we use a PID controller? Well, we said that with the proportional gain, the higher is the gain, the faster is the system. So the transient is actually reduced. Transient is also reduced by the use of the integral action, and the derivative term is not really related to it. So it doesn't really make the transient longer or shorter. It's something just unrelated. On the other hand, there's the overshoot. Well, the overshoot, as we've said, with the proportional controller goes up, because the overshoot is the oscillation before reaching the steady state, whatever it is. And we said when we use a very high gain in the proportional term, the system actually can oscillate a lot. It's faster for sure, but it oscillates. And again, with the bicycle, it might cause oscillation, and then might also cause instability, but it goes it oscillates a lot. Oscillations are also present when using an integral gain, but again, the derivative term, remember, acts as a brake. So it's something that breaks the system, and therefore the overshoot is actually reduced. Now, the PID as is, which for what we've seen so far, sounds pretty solid, but it has some problems anyway. One big problem that is present in the PID is the saturation and wind up. So saturation is referred to actuator saturation. So it might be that you are controlling a system, whatever this system is, and you have some motor that is actually the real controller, so that is giving the control action. And for the state of the system that maybe is very far away from the set point that you want to achieve, or whatever is the situation, it might be that actually what happens is that the control signal that you would need in order to control the system appropriately is actually above or below, so anyways is beyond the capabilities of the actuators. So you need more than the actuator can give, or you need less than the smallest amount that the actuator can give. So the actuators are saturating. Well, what happens? What happens if the control action that we need exceeds the limits of the actuator? Well, it happens that we have saturation signals, because the motor cannot provide more than whatever it's specified, right? And therefore, we have that the input that we're giving to the system is not what we expect. So we compute something that would stabilize the system, because it's computed with all the techniques that we've seen so far and more, But this is not really what we're feeding to the system, because we are not able to achieve that kind of signal. So the actual input will be different from the computed one. And basically what happens is that we have an open loop evolution. At that point, we don't know, we have really no power anymore, because the open loop evolution, if you remember the very first lecture, is something that you have a process, you try to control it, but you don't really care about the output. You just try to control it. And it was like the example that I made there, I think it was with the heater at home. So you are in a room, you're cold, you turn on the heater, and you don't measure how much the temperature is now. You just say, oh, is it warm enough? Yes, okay, then switch it off. So it's a sort of open loop evolution. It doesn't try to achieve a certain set point. And this is exactly what happens when you saturate the input, because at that point, yes, you are measuring the output, you are computing the optimal input, but you're feeding something else. So in the end, it's still basically an open loop evolution. And this can be a problem, because it might be that the input that we're actually feeding, which is the saturated input, makes the system unstable. So it's not able to stabilize it anymore. Realistically, like concretely, what happens is that usually the process slows down. So reaching a certain set point or whatever you're trying to achieve is something that gets way slower, because you are not satisfying the requirements that are set by the error and all the evolution. But in some cases, it might actually lead to instability. So basically, this is something that then can cause the wind-up. So let's explain a bit the wind-up. So the wind-up is, we have a rapid change of reference. So you have something that is happening, the reference changes rapidly, and the error so is growing, right? If the error is growing, we know that the proportional controller does its own stuff, but the integral action starts accumulating, right? The error is growing in time, because like if the reference changes very, very rapidly, then we are not able to follow it immediately. So there will be a big error for some time. And in this time, the error accumulates. So the integrator, accumulates. It accumulates the error. And so it basically tries to give more and more and more input all the time, because it has to compensate for that error. So at some point, we might hit saturation state. When we hit a saturation state, and eventually, like we keep doing our thing, the system keeps evolving, and then the error that we have starts going down, eventually approaches zero. But because of the saturation and because of all this accumulation of the error, the integrator is still discharging. What happens then? It happens that the integrator is not aware of, we have zero error, I need to switch off. The integrator still sees all the past and sees that in the past time you had a lot of error, because it tried to basically annihilate that error with a huge control action that was not matched. So the approach to error equal to zero was a bit slower than expected. And therefore, it keeps giving a lot of input, because it has to finally discharge. It has to have the error going to zero again. And this causes overshoot, more actuator effort than necessary, because you've already hit the set point, but you keep controlling the plant like crazy, the process like crazy, because you want to discharge the integrator. And it's actually like a problem, because it might make the process continue evolving, and this might harm the system in general. So this is the wind-up process, and it's actually the main disadvantage of the PID controller. Of course, there are some ways to reduce it or to try to control and smoothen this process. And some of this is not really part of the course, but I'm going to mention for those who are curious. One is called conditional integration, and basically is we have this problem here that when the integrator charges, it might saturate and then it keeps going on. Well, one thing you could do is that when you saturate, you just switch off the integral part. So the integral is not active anymore, it doesn't charge, so it doesn't have to discharge later. So when we hit saturation, we'll just enter a safety state where the integrator does not work. We just rely on the P and in case the D controller, and as long as then the input is not saturated, the control signal, exactly, the input is not saturated anymore, and we keep evolving. Another way to try to handle the windup is called back calculation, and this back calculation is basically just another control loop just around the integrator part that tries to avoid open loop dynamics. But this is some like advanced control topic, which is not really part of the course. We're going to see an example of the windup later anyway. I'm going to go forward with PID parameters because for now we've seen like how the three actions work, what are these three parts, but we've also seen there are some parameters. There's some gains, some time constant, and the thing is, you have a PID controller, you buy it or you build it, and you need to set this constant, and the problem is how do you tune these parameters? This is something that is actually usually done via heuristics. So you see actually in simulation how the process works. There is one method which is called Ziegler-Nichols table, which is the most known, most common way to at least have an initial guess of how to tune the PID parameter, and it gives you some guidelines for setting the three gains in case you're using just a proportional controller, PI, or a PID controller. And we have some constant which depend on the system, and they're basically the zero state gain of the system and the time of evolution of the system. But this is like just one way to tune it, is like common in the literature. So I wanted to mention it here in order that you know what this Ziegler-Nichols table is. Let's go on with some examples. So we want a position control task. This is actually a task which is quite similar to what we've seen last week with the parking. So we have a robot or a car, we want to move it to a certain goal location, and we want to generate the control U that makes the car move to this location. We have the location is estimated by a sensor, so we have some sensors on the car that allows us to know where the car is, and we want to generate this input. We can simplify the problem. The problem can be simplified to a point mass, so our robot just collapses to a point, can move anywhere in the space, so it just moves. It has a mass, it has a certain position x, and it has certain velocity. So the position control is the task of reaching a certain desired position, stop, so it's actually the parking. At each time instant we apply certain control, we want to use a PID controller. This is our setting. What happens? So first we have the model. The system model is the simplest physics model that you can imagine. So we have that the position where you are at certain time t depends on the position where you were at the previous instant, plus the integration of the velocity over time. So you have the velocity multiplied by delta t, which is the length of the interval. And in this case, we assume delta t equal to 1 second for all the simulations that we're going to see here. So it means that basically you compute a certain control action and you apply that for 1 second. And then after 1 second, you compute the next control action and you go forward. The initial state of the system is the vehicle is in zero and it's just still. So it's not moving. And the simulation says that if it's not moving, then we know that for the Newton's law, it doesn't move. So nothing is applied on it, nothing is happening. So the velocity is zero, position stays in zero, nothing is happening, and there's no control here. So this is no surprises here. This is basically the rest state of the system. Okay, now let's try to control this system to achieve this parking with a P controller. P controller is a proportional controller, as we said, and we have U is equal to K error. Error is the desired state, so the parking spot, minus the current state, so where the car is at the moment. And we see that this is what happens. So basically what happens is that we have a certain position X, which is the red one, which is this is where the car is, and this oscillates around 1, which is this line here. So it doesn't manage to park. Why does this happen? Well, it happens because the controller sees an error here and tries to steer the control action in the opposite direction. But then at some point it hits zero, but the controller doesn't stop immediately because there's some evolution going on. And so this keeps oscillating in opposite direction and never stops. So the problem is that basically the controller detects the new error that it has every time and tries to steer the system in the opposite direction, and this causes the oscillations. So we have the red, which is the position, blue is the velocity. So basically you can imagine as if the system tries to park and starts oscillating around the point, which is the desired state, and doesn't manage to stop. And the input is also oscillating. The green one is the proportional action, the other actions are at zero. So you can imagine here what we need is something that manages to make the steady state error to zero to break the system. So actually we try with the derivative term. Why the derivative term? Because the proportional action is something that makes the system oscillate around this desired state without managing to stop. But the derivative action acts as a brake to the system. So actually this is something that when we approach the error, we see the evolution of the error, we see in which direction it goes, we see that it's maybe a bit too steep, and so the controller is actually giving a control action which is a bit too strong for the state we're in, and so this makes the system break. This is the idea that we presented in previously, and this is what we try to apply. So we have the proportional controller and we have the derivative controller. The derivative controller is a difference also in the velocity. So another way to interpret it is that before, what we've seen was that the system was taking care of the difference in the location, but it was not aware of the velocity. Since it was not aware of the velocity, what was happening is that the velocity, when it was hitting zero error, in the instant the system was passing through zero error, it still had a velocity because that was not controlled. And so the system was kept moving. And at some point it was stopping, because it was detecting the error, going in the opposite direction with the opposite velocity, so velocity with opposite sign. And again, when the error was at 0, the velocity was still not 0, because the control system was not aware of the velocity. So in here, we are trying to be aware of the velocity as well, so that at some point we see, okay, we are approaching 0, the velocity is whatever it is, we need to annihilate this, but also annihilate this, because velocity is part of the state. I want to stop there. I don't want to keep moving. This is what happens. So we actually have now, we solved the control problem. The position goes to 1 asymptotically. There's no error anymore. And the velocity eventually goes to 0. We have now terms, like the red one is the proportional gain, the purple one here is the derivative gain, and so the dark green one is the total control action, which is composed of the two components, while this light green, which is still at 0, is the integral part, because there's nothing happening here. Notice also how, like, this is solved in less than 10 seconds. So 10 is here, so this approaches steady state slightly before 10 seconds, because it's something that we will actually see now. Because we have these two, and what happens with high gains? So Kp and Kd, we just put it up as much as we want. But it happens that the system is still fine, but there are some oscillations, because we know that now when Kp goes up, the system might oscillate. So there's some overshoot, some oscillations, also the velocity oscillates a bit. So you can imagine that you're trying to park, you go, but then instead of braking perfectly as we did before, we overshoot a bit and then have to go down. So this is basically what's going on. This is with high gains. On the other hand, with low gains, we see that the system is still fine, everything is fine, but now the steady state is reached at almost 20 seconds. So low gains make the system way slower. And the thing now with gains is always, this is also why there's heuristics for tuning the PID parameters, and one does not follow exactly whatever it's written in the Ziegler-Nichols table, or just fixing the parameters once and for all, is that there's always a trade-off between velocity and overshoot. So you always have to play with the gains a bit in order to gain the desired performance, because depending on what kind of system you're working with, you might want it to be as fast as possible, even if there are some oscillations, or slow but safe. This depends if you're working on a power plant, or if you're working on balancing something, or this really depends on whatever the application of the controller is. So far, we have not used the integral part. The integral part, we said, that has the big advantage that makes the steady state error goes to 0. So far, the steady state error goes to 0. And so what is the problem? Why would we use the integral error? Well, imagine the case in which we have a systematic bias. So, for example, we have errors which are very typical errors. For example, the robot wheels are not the same size. One is slightly bigger than the other one, or is more inflated than the other one. Or there is, for example, the weight distribution of the robot is not perfect, so it's not perfectly in the middle, but it's more on one or the other side. And so there is one dominant direction for when the robot is moving. These problems are not captured by the kinematics. When we use kinematics model, like the unicycle, the bicycle, or all the ones that we've seen last week in the last lecture, those errors are not described. And so it's not something that we would not be aware of, and we need to take them into account somehow. So this kind of error is something that causes a systematic bias, so a systematic offset from the desired state. So in this case, for example, we might have that the evolution is exactly what you've seen before, but there is a steady state error. And the idea of the PID controller, so with the integral action, is that we are actually able to estimate this systematic error. And by estimating the systematic error, we can have a behavior which is like this. So this basically integrate the area under the curve. It notices that there's some error and it tries to reduce it. It doesn't matter that the error is given by the fact that one wheel is bigger than the other, because the PID controller is just aware of what's going on, what happened in the past, what's happening in the present. So it manages to deal with this error. And this estimation of the systematic error is something that is useful for this kind of system in order to reach a steady state. But it can be dangerous for the windup. What do I mean? Well, imagine the case you have a robot moving, and the robot at some point is just stuck in a hole. So the wheels are moving because you have a sensor reading that tells you where you are. So the wheels are moving, the state is not changing, and so the error starts going like crazy, because the error goes up and up, because the desired state is probably like somewhere else, because the robot should have kept moving, but is not able to move because it's stuck. So there's a huge difference between where you want to be and where you actually are. So this is now growing. And since this is growing, errors keep adding up, and the integral term starts charging and charging and charging, and it becomes something very, very big. So this actually hits all the saturation, wind up, everything that we mentioned before. So imagine that then now at some point, the wheels keep turning, and at some point they manage to unstuck. And so the robot is now back on track. And now it has an insane velocity that is commanded to the robot in order to compensate for the error that it had so far, because there's a huge error now which is caused by the fact that it was stuck in the hole for some time. So this might damage actuators, and what happens is that what one does usually is trying to integrate in windows, in shorter time windows. The problem with this is that this integrates from 0 to t, so it integrates the whole time. If the robot is stuck in a hole and is stuck in the hole for some time, the integral term keeps charging and charging the whole time continuously. And what you can do is to limit the integration to a certain time window, so it just charges for a bit. And so there will be like a bigger input given to the robot once it unstucks, but it's not an input that has to compensate for the whole time that the robot was stuck. It's just an input that will drive the robot a bit faster so that it starts compensating, but then this compensation goes also on in time, and it's not just one super big impulse to it, but it's somehow distributed in time. This is an alternative to the techniques that I've mentioned before about, for example, having this conditional integration where you see the robot getting stuck and then you just switch off the integrator, because in some cases you actually want the integrator to be on and you want the robot to be able to compensate for the error that it accumulated so far. Just you don't want it to go crazy while moving because of an insane control action and you're feeding to it. So this is an example on parking that we've seen when one or the other component is useful. Now, just to have a final wrap up, when do we use one or the other controller? So this is something that just you can see as the takeaway message for the PID controller. So P, proportional term. We want to reduce the rise time. We want to stabilize the system. we don't have really a steady state requirement, so we don't care that the error actually goes to zero. We just wanted to, we want a simple approach, easy approach that makes the system fast and kind of stable. However, what we get is steady state error, and doesn't dump oscillatory systems. So if the system oscillates, it keeps oscillating. And if we exaggerate, we might actually harm the stability. So then we actually go against what we wanted to achieve with it. Then we have a PI. PI is, we want to annihilate the steady state error. So we have some requirements there. We need to track something. We need to hit a certain set point with no mistakes. We use the integral term. We don't care if the response is slow or like maybe we don't have any oscillation, like it's just like something that goes to the set point smoothly and stays there. This is the kind of system that we want to use the PI controller for. Problem is, depending on the time constants, integration time and everything, we might introduce overshoot, and the transient doesn't really improve. So if we're fine with being slow, then it's okay. The thing is that if we try to be faster, then we might introduce a lot of oscillations, and this has to be a compromise, I would say. So something to keep in mind. PD that we used for the example before, we have a good transient. We have basically, we can basically reduce the overshoot to zero because this damping effect from the derivative term is able to deal with the overshoot. But again, we have no steady state requirement. So this leads to steady state error. It might lead to steady state error, as in the case of the systematic bias we've introduced before. And also it's sensitive to noise. So this PID controller is something that's very sensitive to noise because this derivative action is a very delicate term. And again, remember also I said when I introduced it that it amplifies all high frequency noise, and is something that might become harmful then at some point. And finally, we have the PID controller. PID controller puts everything together, so it's the best from all the terms. We have a good transient, we have no error at steady state, we can have the system which has no oscillations, no overshoot, stable, but also fast. So it actually puts everything together, and you have a very, very good controller in your hands. However, it can be complex to tune because, again, I mentioned the Ziegler-Nichols table, but is not something to follow like all the time completely for all systems. It is something that depends more on the kind of system that you're working on, the kind of requirements that you have, what is more or less important to achieve. And so it has to be like a complex playing with 3 parameters in order to find the perfect configuration. It is sensitive to noise. Again, this is something that is not really solved because unfortunately this something is there. It's caused a bit from the D term, from the derivative term, and also in general we haven't really dealt with the measurement noise that I introduced in the big block scheme. And also the PID, I haven't written it here, but I think that now you have an idea of the fact that the PID might have the wind-up effect. And so it's something that you have to consider, something that you have to deal with. You have to decide how to take care of the integrator part when the saturation might happen, if it can happen in your system. So this is something that has to be taken care of. So, summary, we introduced the PID control, all the different terms, all the different components of the PID controller. We try to describe the contribute of each individual term, and in the end there was the windup and an incremental example where we've seen how the P performs, how a PD, PI, PID, and everything. We also mentioned what can the windup effect cause, and finally just a recap of everything that we've seen so far. So again, use some references. Also, PID controller, as I said, is the most common kind of controller that you can find. So you will find a lot of material on it, and I invite you to just check it out and also have a look at anti-windup effects and anti-windup techniques mostly, because they're not strictly part of the course, but it's something that can always turn out to be useful for actual control systems. And I will see you on the next lecture on digital control systems, on discrete time systems, for the 5th lecture of our course. Thank you for your attention.